Represent the logic gates in the figure 3 using a truth table. So in this figure, we have been given a logic gate symbol. A logic gate which contains several, or rather, we have been given a logic circuit. The right term to use is the logic circuit. And this logic circuit contains several types of logic gates. So, when you are taught to draw the truth table for this, you have to know actually what we are doing. We are drawing a truth table for to determine the output of the logic circuit K. So you have to know at every gate that is used, at the end of every gate, you have to know the output. And to know the output, actually you have to know the kind of gate that is used. So let's redraw our diagram. Let's redraw our diagram. So when we redraw our diagram, it will look like this. We have the first gate is an AND gate, so we shall redraw it. We have, this is E and this is F, so we have AND gate there. Then this AND gate, its output goes to other two NAND gates. The other gates are called NAND gates because they have a bubble at the end, and this bubble means we have a NOT gate connected at its end. So we can actually draw like this. So here we have input G. So we will not have the bubble, we will write it, then we have a NOT gate at the end. The bubble indicates a NOT gate, so we are going to redraw the diagram in order to make it simpler. So that is another AND gate, and with a NOT gate at the end. Now from there, these two are going into what we call XNOR gate, whereby XNOR gate, it is an XOR then plus a NOT gate at the end. So we are going actually to separate them. We are going to separate them so that we have the XOR gate and the NOT gate alone, so that at the end of it we have our K, which is the output. So to draw the truth table, we have first to determine at the end of every gate what is the output. So this AND gate will give us EF as the output because we are doing logical multiplication. Then this EF will get inside here and inside here. Together with for the various gate, we have another additional input G and H. So for this one, at the end of it, so we are having EF as the input and H. So at the end, we shall have EFH. So here we shall have EFH. This EFH will go inside a NOT gate, and at this point we shall get EFH then negated. Also for this we shall have EFG, and at this end we have EFG, which is negated. Then this negated and expressions, they are taken inside an XOR gate. When we don't have a bubble, it is called XOR. So this is an XOR. When we had the bubble is when we have XNOR gate. So we take the two inside an XOR gate, and what we get at this point is EFH. We have negated, then we represent XOR operation like that, then XOR EFG like that. So that is the expression there. Then this expression will go through a NOT gate, and we will get EFH negated. We XOR EFG, then the negated will have an overall negation symbol. So those are the various expressions that we get at the output of every gate. So now after that, you draw the various inputs and outputs. So for this case, to determine the number of rows to use in the truth table, you have to know the distinct inputs that have been used. So in this gate, we have used 4 distinct inputs, which is E, F, G, and H. So in that case, we use the formula of 2 power n to determine the number of rows, where n is the number of inputs, and this is 2 power 4. We shall have 16 rows in our truth table. So let's draw our truth table with 4 inputs, which is E, F, G, H. So we shall have E, F, G, H, so we have those. Inputs. So let's draw. So these are our inputs. So we are going to have 16 rows in our truth table. So you start from the first input E, and you alternate. So in truth tables, we normally write the total or the maximum possible combinations of the various inputs, and that is why we have the 2 power n formula. So in this case, you start from the first one, so we shall have E having 8 0 level and 8 logic level of 1. So we shall have 0, we have 0, 0, 0, 0. So we have 8 of them, so that is 4, 5, 6, 7, 8. Then we have 1, 2, 3, 4, 5, 6, 7, 8. Then for F, we go with 4 zeros, 4 ones. So we have 1, 2, 3, 4. 1, 2, 3, 4. We have 1, 2, 3, 4. 1, 2, 3, 4. Then when we go to G, we go reducing. So we go for 2 zeros, 2 ones. So we have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Then we have 1, 2, 1, 2. Then for H, we go now with 0, 1, 0, 1. So we have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. We have 0, 1, another 0, 1, and another 0, 1. So that is basically the truth table, which is now the inputs. Now, what we do next, considering our modified diagram, you write all the outputs at the various gates. So we shall use the EF, we shall add column for EF. We add another column for the one which has been negated, this one, which is for the whole NAND gate before separation to NOT gate and AND gate. Then we go to this and we have another column for this. We do that to simplify the truth table. So we had a column, so we are referring to this diagram. So you had these columns. So we had a column for EF. We had another column for EF G negated, another one for E F H negated, another one for the XOR operation, which is EF G negated XOR EFH negated. Then lastly, we have the output, which is EFG negated XOR EFH negated, then an overall negation like that. So these are the columns that we have. So let me draw the lines. So as we shall see, when you have the outputs of various gates at every stage, it becomes simpler. So now, what we do now, for this expression, now we don't refer to our diagram because we have the expressions. This is an AND expression. So we take the values of E, we AND them with the values of F. So we know the rules of logic multiplication. We have a 1 where the inputs are only 1. So if both inputs of E and F are 1 is when we have 1. So EF will be for 0 and 0 we have 0. So where we have two zeros, actually we shall have, where we have two zeros or either one of them being 0, we have a 0 at this column. So we shall have 0, 0. We have 0, 0, 0, we have 0, we have a 0, a 0, another one, we have another one, you have 0, 0, then we have 1, 1, 1, 1. This is because E and F are both 1 at these columns. So that is that column. Then for the other column, we are taking what we have gotten in this column, we pass it through an AND gate together with the inputs of G, and after that we negate what we get. So for example, let me show you the first one so that you can feel very fast. So for example, we take 0 and 0. 0 and 0, we get a 0. Let me show you. So in this one we are saying 0 and 0. 0 multiplied by 0, we get a 0. When we negate this 0, we get a 1. So in this case, we write 1 because we are negating the output, which is 0. So for every output that we get, we negate it. So next we have EF is 0 and G is 0, so we have 1 also. And when you consider that kind of a scenario, you will find that we shall have ones all through but for the last two we have a 0 because when we consider G is 1, EF is 1, G is 1, EF is 1. So in this case we get an output of 1, then we negate 1, we get 0. Let's go to this column. In this column, we are getting the column of EF that we have gotten here, and we AND it with H, and we negate what we get. So it is the same as we did for EF and G. So for EF, for example, in the first one is 0 and H is 0. So in that case, 0 and 0, we get 0, then we negate, we get 1. So when you use that method, which is the same for the previous column, we will have 1, 1, 1, 1. So we shall have how many ones? 14, that is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then after that, the last two, not the last two, we are on H. We are on H, so let me undo this. So we are in this column. So the first one, we said it is 1, so we shall have 1. We shall have 1, then we have 1. We have another one. 1, 1, 1, 1, 1, 1. We have 1. Let's check first the ones with the ones because the table here may not be uniform. So we have a 1 up to this column, up to this row. So the last one is 0 because we have EF. EF is 1 and H is 1, so we get a 1, then we negate it to get 0. And the one above there is H is 0 and this is 1, so we get 0, then we negate it to get 1. Then above there we get a 0. Then all the others will be 1s. So only these two rows will have a 0. When you draw the table systematically in a ruled paper, you'll get the third last will have a 0, and the last one will have also a 0. So let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They should be 16. So make sure you draw 16 rows. 16 rows. So let me have the other 13. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then we have 14, 15, 16. So we have that. We have 1, 2, 3, 4, 5, 6. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is correct. Let's go to the third one, the other column, this one, where we are doing the XOR operation. Now, for these operations, you have also to know how they operate. So for an XOR operation, which is represented like this, in this XOR operation, whereby the inputs which have been applied are of different logic levels, is when we put a 1. For example, 0 XOR 1, this one will give us a 1, and 1 XOR 0 we give us it gives us a 1. So at the point where we get the inputs having same logic levels, like 1 XOR 1, we get a 0, and 0 XOR 0, we get also a 0. So when we use that concept in this column, actually because I said when we do this like this, you simplify the truth table. So we are now considering only this column and this column. So where we have the inputs having the same logic level, we put a 0, and where they are of different levels is when we have a 1. So when we consider this, you'll realize that we shall have only a 1 at the 15th column and the 14th column, because at these columns we have different levels of the inputs applied. Remember, these are the inputs applied to our gates at this point. So we shall have 1s there, and all the other columns will contain a 0. So we have 13 zeros now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that is how now we do for that. Now for the last one, it is very simple, because we are only taking this expression and we negate it. So we are only negating the outputs here. So for these outputs, we know that when you negate 0, you get a 1, and when you negate a 1, you get a 0. So we shall have at this point here we shall have 0 and we shall have a 0. Then all the others will be 1. So here we have 1. Then we add other 13 ones. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that the total will be 16 rows. So that is the truth table. We may have taken long, but if you follow it keenly, you may be able to draw even for other complex circuits. So that is all about that truth table.